Like I do understand it's very diverse audience, just by judging by the people that I know. So I do hope that there's a bit for everyone in this talk, and I can well give you an idea why the things that I'm interested in, coupled oscillation, synchronization, and higher order interactions, are interesting, and how they actually well link to one another. So I'll keep it light on specific formulas, but there's kind of a lot of mathematics hiding in the background. So I should probably delete this. Okay, perfect. So before I start off, I should say this is joint work with my former PhD student Toby Bulle, who was at TUM. Christian Kuhn, who's also at TUM, the co-supervisor. Then in the middle, there's a bit of joint work more recently with Bob Rink and Babette Wolf. Babette just moved to Hamburg to take up a tenure track position there. And the last bit, if I have time, this is not in the title, is joint work with Søren van der Gracht, who's in Paderborn. Of course, if you have any questions or whatever, please feel free to interrupt me. I'd rather have a bit of an interactive talk as rather than seeing lots of super confused faces. Obviously, yeah, we'll constrain this a bit, but do interrupt me. Okay, what is one of the things that I'm interested in? I'm interested in coupled oscillators. What is an oscillator? To me, an oscillator is a periodic process. Right, something that evolves topologically on a circle because it repeats itself, right? And these things come up in various applications. So I can put my mathematician's hat on and say, well, I'm interested in coupled oscillators independent in quotation marks of the application. Talk about this in a little bit more detail in a minute. But of course, since we're in the Netherlands, the first example that I have to mention are, well, basically coupled metronomes and Huygens' strange sympathy between coupled pendulum clocks. So basically, you take metronome of two clocks, that's a periodic process, hopefully. And you put them together on this beam, and because energy can be transferred from one to another, what Huygens observed was this synchrony, or in particular anti-synchrony between these two clocks. So you have your first example of a collective phenomenon. Individually, while these things are periodic processes, they go around, you know exactly what they do. But what you're kind of interested in is the collective dynamics. Emergent collective dynamics, if you like it, but that's kind of the things that don't happen when you just have one, right? Similar things happen to an approximation in the brain. Are there any neuroscientists here? Well, no, you don't count. So suppose you have neural cells that are tonic spikers that do a perfect oscillation, which obviously they won't do, but assume that you do. You can see the brain to a certain extent as coupled oscillators. That's on the neuron level, but maybe you have coupled oscillations in terms of local field potentials, brain regions, whatever, and you couple them, and that gives rise to the neural rhythms that are linked to functioning. So, I mean, if you talk to neuroscientists, they say oscillations in the beta band, whatever that is related to disease, non-disease. And then more recently, we'll talk about this in detail, is like power grid networks, where you can see in a very simplified way a generator or motor as something that goes around the circle. You have lots of them in a country. I gave this talk in Laos at some point, so I still have the map of Laos here. So basically, you have a couple of oscillators that are energy sources that pump system energy into the system, and then you have consumers like us that just want to plug our computer into the power outlet. And of course, you have to keep your power grid in sync frequency-wise, because whether you use the plug here or over there, it's always 50 hertz here, right? So frequency synchronization is something that is related to the stability of the power grid. And there's lots of fancy engineering that tries to control grid frequency and keep it stable. Okay, so that's another example of just a qualitative example of a collective effect of interacting oscillatory processes. Okay, So kind of taking a more kind of mathematical point of view, that's what's my cartoon that describes this. I like to think about things in terms of networks. So, well, forget about the specific application. Each one of these blue dots is one of these physical systems, or more precisely, model equations that might approximate the physical system. And then they interact, right? So in my cartoon here, these are my little oscillators that they might have a spatial extent, like this. Well, they might be distributed on this, well, in space or not, doesn't matter. But they basically interact along these lines. And there's two main ingredients for me that kind of determine the interactions. On the one hand, there's the network structure, the network topology, who talks to whom. So if you talk to a traditional network scientist, that's what they're interested in. You look at a graph. The graph tells you, well, who talks to whom, who interacts with whom, and then you extract centrality, whatever you like, out of this graph. That's kind of more the structural aspect. For me, as a dynamicist, I also have to care about the network interactions, because each of these things is now a dynamical unit. So it's given by a state in some potentially high-dimensional state space. So I need to know how the state of one node influence the state of the other node. And that is a functional relationship. So basically, I have to say, how does, if you think about differential equations, how does the state of one node affect the state of the other node? So that's basically something about the right-hand side of your differential equation. Yes?
I see here symmetric arrows. Do you assume that the interactions...
Not necessarily. So this is just my cartoon. We'll talk about network structure in a minute, but well, you can have symmetric, you can have non-symmetric interaction, you can have adaptive interactions. I won't talk about adaptivity in networks, but these are all questions that you can look at different aspects. So this is really literally just a cartoon. Okay? And the overall question is kind of this general question that is too general to be answered, is kind of how does network structure and interactions together shape the emergent network dynamics? So what comes out of this? So how do these oscillatory processes behave together rather than by themselves, right? So that's really the question. Well, yeah, the system is more than the sum of its parts, because synchrony can happen. Okay, we'll talk about higher order interactions and what this is and what it's not, at least for me. But let's start off with the standard kind of, maybe a standard approach for like pairwisely coupled networks. So start off with a graph. A network of pairwise connections. So each node here, K, has an edge between L and K, and J and K, and so on. So that kind of indicates, if you look at this from a combinatorial point of view, that somehow node J influences node K, and node L influences node K. But since they're edges, so maybe I should...
just double click on the slide.
On the side.
On the slide.
On the slide. Oh, double. Yeah. I should. Is there like something that keeps me from touching the touchscreen? Maybe I should point with this thing. It's like it's not as much of a sausage as my finger. So basically, that kind of suggests that somehow the interaction, this edge here, has nothing to do with this edge here. So somehow the influence of J onto K and the influence of L onto K should be independent of one another. And that's a typical assumption that one does. So now you have here, it's an oscillator. So, well, it's a circle basically, right? And somehow you have now an influence of the state of oscillator J onto the state of oscillator K that comes along each of these edges. And typically you just add them up. So you have a superposition of all the individual influences, right? So that's a standard assumption. And if you, yes?
Are you assuming that all these oscillator units have the same frequency?
That's the typical assumption I would make. In the power grid networks, you don't have this because you basically have some units that put energy in and some that take units out. There's in this example, actually, that I'll talk about in a second, you actually don't assume that they have the same frequency, but in some of the math that I'll talk about, I typically make this assumption. I'll come back to this later. But it's a good point because here is kind of my cartoon of the Kuramoto model. Who's heard of the Kuramoto model before? A number of people. Okay, well, the Kuramoto model is basically you take a whole bunch of oscillators that are globally coupled, so everyone talks to everyone, and this interaction function G here is a sine function, pure sine function. And they are non-identical, these oscillators. So Kuramoto assumed that they're from a unimodal distribution, so they have a single peak, and they're kind of there's some oscillators that have like very high and very low frequencies, but there's like a single frequency peak. And the idea is now, okay, well, what happens if you crank up the coupling strength, right? So if you crank up the coupling strength, then at some point you have a critical coupling strength before, if the coupling is too weak, your non-identical oscillators will just rotate independently of one another. They cannot phase or frequency lock, right? But at some critical coupling strength, they will start locking, and the oscillators that have nearby frequencies will form a cluster that then, if you increase the coupling strength further and further, will become more and more synchronized. And if you send the coupling strength to infinity, then we'll have a synchronized cluster because coupling dominates anything, right? So this is the cartoon here on the, well, they say it's not a cartoon, that's kind of the bifurcation curve that you get. Here on the y-axis, you have the order parameter. So basically that gives you, is a measure of phase coherence in the system. Here's the coupling strength on the y-axis. So if you have a, below threshold coupling strength, you have 0. So that is incoherence of the oscillators. They don't lock. And then you basically, as you increase the coupling strength, you get this cluster that synchronizes and synchronizes more. And at some point captures all the oscillators that then first frequency lock and then phase lock to the main cluster. That's the standard thing. So that was my 1-minute introduction on the Kuramoto. Yes?
Maybe a question there. So this assumption of the Kuramoto model assumes that the amplitude of the oscillators doesn't change, right?
Yeah, so you can motivate this, and I'll talk about the motivation as a phase reduction for weakly coupled oscillators. So these are pure phase oscillators, but I'll talk about the connection in a minute to amplitudes as well. So what I want to get now is a generalization of the Kuramoto model, because people like higher order interaction. So from this perspective, what is a higher order interaction? So you can generalize the Kuramoto model. So here's my Kuramoto model, still with the edges. I hope you can see this despite me standing in front of it. But now you might not only want to have additive interactions between pairs of oscillators, but you want to have a non-additive interaction that depends on multiple phases. So many people have proposed generalizations of the Kuramoto model. So they take Kuramoto's equation, but they add additional terms that basically now have a coupling function h here that depends on, say, 2 times the phase of that oscillator minus the phase of that oscillator minus the phase of the oscillator that it's targeting. And if you like combinatorics, you could see this as an interaction that you could associate with a hyperedge or a simplicial complex that kind of fills in this case, this clique. But I mean, this link is not necessary. So it could be a general hypergraph. So basically, the idea is that if you have a graph, then you assign pairwise interactions to each of these edges. And if you want to, then they're additive. And if you want to have non-pairwise interactions or higher order interactions, then you have to generalize your combinatorial structure. Yes.
Here is asymmetric in exchanging I and L.
Huh?
So K is within the little circle is theta K.
So I mean, that's a good question in terms of the. So this is not symmetric in terms of L and I, because in some sense there's the 2 theta L minus theta J. So if you swap the two, then basically that kind of swaps these two, which kind of opens up this question, okay, well, if you have a hypergraph, then typically you don't have an ordering. So maybe you should not only add this interaction term, but also the one where you have them swapped, yada, yada. Or you invent new forms of hypergraphs that are directed, where your edges are not sets, but tuples that have a particular ordering, and so on. I'll watch this. I'll put this under the table for now. If we get to the bonus bit, I will elaborate on this in more detail. But it's really the question, okay, well, you have to take a hypergraph and then you have to make a decision what my interaction function will look like, right? So you could also take the other. Yes?
Why do people like higher order interactions?
Let me get to the last bit of the cartoon. So for example, you see new effects. Right? So one thing that people have then observed, okay, a Kuromoto basically says a continuous transition to synchrony, right? But if you add these higher order interactions, or certain higher order interactions, you can have a discontinuous transition to synchrony. Or some people like to call it explosive synchronization. Because if you slowly ramp up your coupling strength, you fall down this branch and you have a rapid change of your system.
Actually, the quantity you show here is the growth rate, or what?
This is the order parameter. So this is my measure of synchrony in relationship to the coupling strength. Right? So that's one of the things that people say, oh, yeah, I can get explosive synchronization if I add higher order interactions. But you have several choices, and some of these we have discussed. What is your interaction function? What is your hypergraph? And it's not necessarily clear why a particular choice is a good choice. You just take your Kuromoto model and you generalize it in your favorite way. You can do this, that's fine. And then you can link potentially properties of the hypergraph to these emergent dynamics. Yes?
Do we have examples of this explosive synchronization in nature?
Let me get to this on the same slide. I don't even have to, I could just answer questions and basically go through the slide. Excellent. I'll come to this in a second. Because that's my following slide. So my point is here is the example with the synchronization transition, but you can also get other dynamical effects. So more complicated dynamics, chaos, that was kind of my entry point in this. So we published a paper back in 2016 that basically higher order interactions can give you chaos in the system where without the higher order interactions, you cannot. One example of what can arise. So coming back to this question, why is this important? Because you can also then take a different hat on, put a different hat on. Right now I said Kuromoto model, you generalize the Kuromoto model, and then you see a new effect. But there is a process called phase reduction, and this is what I'll talk about, that actually links phase dynamics to, non-phase systems, so real-world, non-linear oscillator systems, right? So actually there is in a certain extent, a correspondence between these phase dynamics, potentially with higher order interactions. And if you take your favorite ODE, like that has a limit cycle, and you couple them in a weak way. And that will be basically the topic for the next 15, 20 minutes or so. So there's a correspondence. So exactly this question, can you see explosive synchronization in real world systems? Yeah, sure. Take this system here in which you see explosive synchronization, find a system that gives you such a phase reduction, and then maybe you see the same thing. And that's actually what people do. I just want to make a remark for the mathematicians. So phase reduction in my, in the sense that I will use it, is basically Fenichel theory plus a limit. So Fenichel theory, I'm talking 1 second jargon now, is basically persistence of normally hyperbolic invariant manifolds. If you have uncoupled oscillators, you have n circles, and circles together give you a torus. And if you couple them weakly, then you still have a torus. But in order to basically then say something about the dynamics on this torus, you have to compute the phase reduction. That's literally this correspondence. So it's basically finish your theory, but also computing the dynamics on this invariant matter. Yeah, there was one more thing that I wanted to say, but it just slipped my mind.
You still didn't say which systems actually show something.
Here, so there's an example here of like this is a paper published in Science Advances about first-order synchronization transitions in a large population of strongly coupled relaxation oscillators. So just by the title, without having made this rigorous, there's two things that pop into my mind. There's the strong coupling and there's the relaxation oscillators. Both are kind of nonlinear effects. And that, in my head, kind of says, okay, well, for strong coupling and strongly nonlinear oscillations, these kind of higher order phase interactions start to matter. And that's why when you see something like this here, you should see something like this here, because these systems correspond to one another. So that's literally the one example, but you can also really do what I've kind of hinted to it before. You can reverse engineer, and that's what people do. Synchronization engineering. So they want to design a system on this side whose phase reduction is this. So there's multiple ways of doing this.
No, I'm still the question. The first question here, like where do you see that? You know?
Nature.
Yeah, nature. Or, yeah,
human
exactly.
problem.
Not a model. Not a
No,
model.
these are experiments. So these are experimental oscillators. We've done the same, but this is kind of in the engineering side of things. You take coupled electrochemical oscillations, you couple them either through a computer or to a wire, and then basically the voltage of one that links to the chemical reaction is linked to the voltage of the other, and you see these dynamics. So I'm literally talking about
current and also, but it's all fake. But
I'll leave it to you.
you actually, is there a phenomenon that we know where this shows up? The brain, I don't know, societal, I don't know, something.
It's just, I mean, okay, well, what's your definition of it being fake? If you have coupled active rooms like
this was designed precisely with the interactions that you wanted. You built.
Oh, this wasn't. So, like in this paper, they made no mention of this. So
No, but maybe they designed with the
no, they don't design anything. There's no phase reduction in there. They just couple these oscillators and they say, oh yeah, and for these strongly nonlinear oscillators, I don't remember what their motivation was. You see these explosive synchronization. And this is my interpretation of this. I say, okay, well, maybe you should look at this from the lens of phase reduction.
I think you could view the starfish as a relaxation oscillator.
Say again?
You could view the foot of a starfish, the feet of the starfish, as a couple of relaxation oscillators. These are like thumbs, tubes, oscillate back and forth, and they're strongly coupled to the flow in the pipes, I guess, in the starfish. I mean, I don't know if anyone modeled it like that. So
Okay.
I think that's
And there's some explosive synchronization.
Well, I'll leave this discussion. I'll leave this discussion for.
Maybe not fake, depending on the fake. Like if you get start with axons and complete fleets and implement the new version of the remote oscillators, you have the first order transition. But I don't know when you will able to get mistake.
Like the question is this still fake? So let's not talk about
Oscillators, you go look at like a football game and everybody doing the wave. Everybody starts out like this, and then all of a sudden the whole thing comes together.
I don't know.
That's but we can talk about this, Brian. I'll put my mathematician's hat back on. I'll put my mathematician's hat back on, and let's talk a little bit about the math that lies behind the two things, independent of the application. Okay, so. Any other?
No, he was still going on with this stuff.
Like at some point, like I want to see this paper. It's already like rolling out in my head. Explosive synchronization in starfish population, like science material. Excellent.
IG no-go.
Yeah. And it's definitely with a quote by Jay, it's definitely not artificial. Fantastic. Yeah. Let's talk about phase reduction and higher order interactions. So there's kind of two ways in a coarse grained setting how you can get to higher order interactions in the phase reduction. And I've always used higher order without actually specifying what I mean by order. It's kind of a term that you use non-pairwise interactions and you call them higher order interactions. So why do you actually call them higher order interactions? So the first way is kind of this relates to this is one example paper by Pete Ashman and Ana Rodriguez, where basically they take a system of oscillators, they have pairwise interactions, and they have non-pairwise interactions. And then they do an asymptotic expansion, so that's where you can define what the order is. And to first order in your epsilon, that's the coupling strength between the oscillators, well, you get exactly what you had before. You get phase terms that capture the pairwise interactions, you get phase terms that capture the pairwise interactions, and you get phase terms that capture the non-pairwise interactions. Duh. So if you have really in the physical system already interaction terms that are non-pairwise, then you expect to see this in the phase dynamics to first. Okay, computing them is still not not obvious. So there's a bit of math. There's this system with symmetry where you can calculate equivariance and you can compute the phase dynamics in a multi-parameter expansion. But the point is that here, this order thing relates to an expansion in small parameter, and here you do an expansion to first order. But there's a second way to kind of get higher order interactions, and that's actually the higher order bit, because that's kind of, you could argue that's not higher order, at least not in the coupling strength, because it's first order, right? Well, you take a system of complicated oscillators, you have pairwise interactions that might be fairly simple, but actually, well, you have indirect interactions. So, well, this oscillator influences that oscillator directly through this edge, but also indirectly because this one influences that one, influences that one. So indirectly, you have an interaction between these oscillators. And if you calculate the phase equations, and we'll do this in a minute, you see that this becomes relevant to second order. So to first order, an oscillator only sees its neighborhood. To second order, you not only see the neighborhood, but also the neighbor's neighbors. There's a slight modification to this, and that gives you a potentially non-pairwise interaction. You could say, oh, well, but the higher order interactions, higher order now, the squared interactions don't matter. Or you could say, yeah, sometimes they don't matter. But if you're close to a bifurcation point, where somehow your first order approximation is close to 0, then the second order interactions matter. So when it comes to transition to synchrony or not, that's where higher order interactions might matter. So let's come to a little bit more the meat of my talk. Yes.
Can I go back to the previous
Of course.
I probably have missed it. So second case, you have two body interactions,
So
but a longer range. It's an only neighbor and then next
so
door neighbor.
here the two like the physical interactions are the purple lines. So these are only pairwise interactions.
But they are not only nearest neighbor, they are also here nearest neighbor.
So, I mean, here you kind of have, like, we'll go into network motifs in a minute, but here it's an all-to-all coupled network. So then basically your pairwise interaction is the direct influence of this node onto that node, and there's an indirect interaction here. But you could also say, okay, well, what if there was no link here? Then you still see this term appearing, even though there's no link here. And I'll cover this in a little bit more detail. But the physical interactions here are only pairwise, but basically the nonlinearity of the oscillation gives you an effective higher order phase interaction. Okay, let's kind of get to the setting where I want to go into a little bit more detail. Phase interactions are a pain to compute. It's really hard work. Higher order phase interactions are even more of a pain to compute because, well, you have to solve lots of difficult equations. And I'll show you an example of an equation where Toby, I was like, I would have given up a long time ago, and Toby did an amazing job at calculating these higher order interactions. So and that's even for a simple system. So let's restrict to a class of oscillators where the oscillation here is almost circular, right? So that's a nice, if you write this down in phase space, think about the unit circle where things rotate. Think of it as Stewart-Landau type oscillator, something that has gone through a Hopf bifurcation where the oscillation is still almost circular. Do not think about, this is a whole different topic, about relaxation oscillations. That's a completely different story. So let's look at a setting where we have simple oscillators with relatively simple, actually, basically just diffusive pairwise coupling. Simple, simple, simple. And let's try to then calculate the phase reduction to first and second order and see what these terms actually are. I mean, this is my cartoon, right? So, but let's calculate what kind of phase interactions we get, what pairwise, what non-pairwise, and so on. And there's three questions I want to touch upon. The first question is kind of the question about the shape of the oscillator. So I said that our standard model is something that is perfectly circular, makes things easy because you have a rotational symmetry in there, so you can simplify things a little bit. But we could think about, okay, well, adding a particular perturbation to this limit cycle. That gives the limit cycle a bit of a shape that breaks the rotational symmetry, say in a maximum of a small parameter, delta. Already gives us two small parameters. There's the coupling strength, in which we want to expand, and there is the size of the perturbation. And see, ask this question, how does the shape of the oscillator influence the non-pairwise interactions? And of course, well, once you have the non-pairwise interactions, you can ask about synchronization dynamics, right? So the synchronization of these phases is determined by the interaction. So then you can say something about stability of synchrony, and that's kind of the emergent effect. So that's the first question I want to look at. The second question is, typically these phase reductions are calculated for all-to-all coupled networks. So let's think about non-trivial networks where not all the links are present. Because if you have all-to-all coupling, then basically a higher order correction might actually just disappear into a connection that is there already as a higher order correction to it. So there we can see that we might have phase interactions that you don't have physically because of this exact, the exact reason that they are indirectly coupled, so through two hops. Third question, and this is the more recent work, is what if you have delays between the oscillators? Well, I kind of like ODEs. They're nice, finite dimensional. If you add delays, then you have delay differential equations. You have an infinite dimensional system. And I'll do some comments about how you can compute phase reductions for infinite dimensional systems towards the end. So that's the more reason.
And what do you mean by the delay?
Delay. So there's basically this oscillator feels the state of this oscillator at the time delay. So there's if you think about delay line or finite transmission speed or whatever, because typically you say it's instantaneous. Mm-hmm. Okay, first question. So let's look at an expansion in now two small parameters. The one is the coupling strength, so something that's related to these physical links. And the other one is basically the strength of the perturbation, how non-circular you make these oscillators. What we do is you start with a circle, you build a model where you can control your perturbation with a small parameter. You can write down this model, and then you can write down phase equations. And that's why I'm saying Toby did a fantastic job, because he computed this. This is the only complicated formula that you will see in this talk. We'll analyze this formula a little bit, but basically you can do it. That's the point. So here my small parameter is not called epsilon, but K for coupling strength. That is assumed to be small. So here basically you have identical oscillators. Coming back to this question, whether I assume identical oscillators. In this case, we do. Also because if the oscillators are not identical enough, then they can't even have phase dynamics. They're non-resonant, right? So in order for the phases to start interacting, you have to have oscillator frequencies that are sufficiently close, that you're basically in an Arnold tongue. And when you're in an Arnold tongue, then you can start to have phase interactions. Otherwise, they will just rotate independently. Now I remember what I wanted to say about the phase reductions earlier. Amplitudes. So maybe it's a good point to make a comment about this. So there was the question about amplitudes and why you don't incorporate amplitude dynamics. Phase reductions basically means by definition that amplitudes are enslaved to phases. So when you know the phase, you know exactly what the amplitude is. That's the existence of your invariant torus. That's why amplitudes do not appear in these equations, because they don't matter for the interactions. Okay? That's an assumption that we make. The phase reduction is valid, right? So of course, if you crank up your coupling strength, you can break the phase reduction. So whatever order you compute is basically meaningless because you don't have an invariant torus. Okay, so just because it came to me, maybe I should make this comment. So you can compute this first order, you get signs of phase differences, additive, you get this correction term that now depends on the delta, and you get lots more complicated things when you take the second order terms into account. And here you have a sine that you multiply with other sines and cosines, and that actually give you, if you know your stuff about trigonometric identities, triplet interaction, sines of three phase. I'll go into this in a second, but you can do this, and that's a nice thing. Does it work? Yes.
How dependent is this like on your specific choice of your ODEs and your interaction terms?
Oh, but this is for this particular model where we can parameterize the limit cycle.
And this is also for Kuromoto interactions with the sines.
So the interactions, yeah, yes and no, because the physical interactions are just diffusive interactions. So in the physical system, the coordinates in xy plane are just coupled to xk minus xj, sorry. So that's just linear diffusive interaction. So the simplest thing that you can think of in physical space. So your physical variables are diffusively coupled in a linear fashion. That's why I said we take the simplest type of interactions in physical space. These are then the emergent interactions in your non-physical, oscillator phase space that parameterizes the oscillation. And now you can pick apart how the complication in terms of the oscillator itself, the physical interactions we keep as these simple diffusive interactions affect the synchronization dynamics. That's what you can now pick apart. Okay. Good. How does it work? Just to kind of give you an idea that sometimes first order phase reductions are not sufficient to describe the system. So what do I have here? Here are the synchronization dynamics, first of the unreduced system here to the left. This green is, I think, synchrony stable. Red is antiphase synchrony for two oscillators is stable, and then synchrony is stable again. And this is the first order phase reduction. Here's the coupling strength, and here's the shape perturbation parameter. And you can see that the first order phase reduction actually captures this bifurcation, the main bifurcation, but completely misses that actually, synchrony restabilizes here, right? Second order phase reduction magically already captures both, and they're quite close. So if you take a particular slice here, you can see that basically linear stability of the system. In second order, you like in the picture norm, you can't really see a difference between this dotted this dot dashed line that is on top of the this solid line there. So first order, forget about it. You get kind of a linear approximation that can only have one bifurcation, right? Because it's linear in that. Here, you capture also the secondary bifurcation. And so in order to understand synchronization dynamics in the system, from the phase point of view, you need to look at the second order phase reduction. But this is kind of a global picture. It kind of depends. If you're only interested in this bifurcation, the first order is sufficient. But if you're interested in also more kind of a more global picture that captures first and secondary bifurcations, then you should do a phase reduction to second order. How do you get synchrony greater than 1? This is not synchrony. These are the multipliers. So in some sense, this is just a measure of linear stability. And if you have this, and I think it's calculated in a return map. If you have something that is larger than 1, it's unstable, and if you have something smaller than 1, it's stable, and that's why this is the bifurcation. I hope this relates to the question.
And what is the excess of the delta?
The delta is the shape parameter. So that's the deformation from the circular limit cycle that you have. Okay. Also, this does not depend on delta, right? So to first order, you actually don't see the shape parameter. It's another thing. Yes.
When you look at perturbations, what kind of perturbation? You look at noise, for instance, or like a more deterministic perturbation?
So this is just linear stability analysis. So this is just, you look at synchrony, you calculate the multipliers of synchrony, and then you plot them, and you see the bifurcation line. So this is not a particular perturbation. This is with respect to infinitesimal perturbation. And it's not the dynamics of the dynamics for particular trajectories.
Quench perturbation, or is it that kind of twisting perturbation?
There's no perturbation. So you take your equations, you take your equilibrium, you linearize, and then you get linear stability with respect to small perturbations. So that's
You're just linearizing around the states.
yeah, exactly. Yeah, that's a question.
Yeah. Can you sort of intuitively understand the difference between the two bifurcations? Why one is picked up by the first order and the other one is only picked up by the second order?
I haven't thought about this. Why you can. I mean, like there is the kind of the explanation that that is kind of the quality of your dependence. So here, your linear dependence is really approximately linear. So it can't have another point where basically it crosses 0. But that's kind of not a very physical explanation, but that's kind of, okay, well, your first order approximation that cannot capture the functional shape of your multipliers that you would need. So that's kind of more the mathematician's explanation.
And this is also very specific to this model, or is it like the fact that only second order captures?
This is, I won't make any statements other than this model. So it's a good question, but have a look. But so this is for this particular model. Since just looking at time, let's look at these two other questions, and I think we can cover them. I don't think I get to the bonus material, but I'll leave it to you to have a look if you're interested. The second question relates to networks, non-trivial networks. So now we have, again, it's exactly the same system. So we have our simple oscillators perturbed by something with delta, but we don't have all the links present. And we want to understand what are now the non-pairwise interactions that come into the system based on certain motifs. And we try to classify this. And this is what you see on the picture. There's two types of motifs that are important. The first row is, so the target oscillator is always K. That's my red dot. So we're looking at how two oscillators I and L influence the state of oscillator K. And there's two motifs that are important. The first one are basically interactions between neighbors. So this is K, and in the neighborhood is I and L. That's the first row. The second one are motifs of two types, like that lie in the two neighborhood of your node K. So node K is connected to node L, is connected to node I. So I've kind of tried to illustrate here, well, the type of interaction, so the size of my blob. Here is the functional form of the interaction, which relates to a question we had before. So what kind of coupling functions do you assign to a particular hyperedge, right? And so for each of these hyperedges, we have to have these interactions. Let's go through this step by step. On the very left, you see basically the same thing. So these are the pairwise interactions that you can draw into two motifs. So this is basically how phase of oscillator L influences the phase of oscillator K, and that depends on the pair of the phase difference. So this is, well, it's not the first order interactions because these are only second order interactions. So this is a pairwise correction to your first order interaction at strength K squared, epsilon squared, depending on how you name your parameter. And of course, this is the same because it's the same motif of a direct connection. Well, then let's look at the first row first. This, in my opinion, is a non-pairwise interaction. It has coupling function sine of phi I minus phi L, but to me this is a non-pairwise interaction because it appears in the equation for phase phi k. So it doesn't depend on the phase phi k, but it's still something how I and L together influence k. So somehow that's a non-pairwise interaction, even though at first sight you could argue it's not, right? So that's the first type of interaction that come in. And the second type of interaction is this type. So this is a true non-pairwise interaction where you have here now phase of oscillator I, phase of oscillator A minus 2 times phase of oscillator K. And that's a joint interaction between the two that comes in at second order. Well, you could say, oh, but these are kind of the same hyperedges. Yeah, that's right. So actually, if you think about this from a combinatorial point of view, if you do phase reduction, you have to deal with multiple phase interaction functions at the same time of different type. So these kind of generalization of the Kuramoto model typically pick one of these interaction functions. But if you link it to this particular physical system, you actually know that both of them come in at the same time. So that's the first observation. The second observation that you can make is that directionality matters. That was also a question before, because here, well, it matters whether you have this motif, but this is not necessarily the same motif for all oscillators. So maybe you should rather see this as a directed hyperedge. So let's not go into the combinatorial details, but the main suggestion is that hypergraphs that have undirected edges are not necessarily sufficient to capture the actual phase interactions, the effective phase interactions that come into phase reduction. Let's briefly talk through the second row. This is the pairwise interaction. This is a funny interaction because it's a pairwise interaction from oscillator I onto oscillator K that does not depend on the state of oscillator L. But there may or may not be a direct link between them. I can give it a fancy name, call it a virtual higher order interaction. And that's kind of a pairwise interaction through L that you see to second order in the phase reduction.
But it's important they are connected through L for the interaction.
So the only thing I assume is the connection from a K via L to I. And if you have this connection, this term will appear. And that's kind of that's one of these funny things when you look at all-to-all connected networks, you don't see these things because you have a link here anyways in all-to-all. So this is just a higher order correction to a link that you already have. So this thing is basically the same thing as this thing because you cannot disentangle the two. But this here is a real virtual interaction that comes into second order that is of pairwise nature. And here you have kind of a funny, just standard high order interaction along the two neighborhood. So non-pairwise I via L through K that interact through these.
Qualitative question, because indeed it's a lot of combinatorics if you go to all possible high order interaction, but after seeing your picture, it looks like this Feynman diagram kind of picture.
Yeah, that's the idea. I mean, this is what we discussed. And the last question is like, can you do this kind of as a building block principle? So you look at your one neighborhood, your two neighborhood, and you can write down the phase reduction based on basically the motifs that you have, and you don't have to compute anything anymore. That's kind of the whole to do.
We will get Feynman diagrams for the higher interaction or something.
I don't know. Do you know more about the like? But the hope is really that you have that you for certain systems. And so this is just an observation for this particular system. That's what comes out. But that's kind of the hope that if you understand your system a little bit, you can stitch together for any network your higher order interactions by just taking the corresponding terms. Yes.
But there's paper by Mark Newman 2 or 3 years ago in PNAS. They developed a systematic method to account for second order, third order neighborhood. So using message passing, you can derive all this kind of neighborhood, and you can account for all the terms.
But yeah, you can calculate the neighborhoods, but you have no idea what the phase interactions are. So yeah, you like the idea.
No, the message passing is very general method. So you define a group of variables,
Yes.
then you write a cell consistency equation for each of the group and how one group affects the other. At the end of the day, it can be generalized for any type of interaction, any dynamical system that you have in mind.
I have to look at I have to look at this particular paper, but to the best of my knowledge, if it rendered any kind of computation of phase reductions invalid, then there must be a limitation to this. So
So at least they demonstrate for computing the spectrum of the graph, also computing the percolation threshold, and using more.
Well, sure. But these are kind of local phenomena. So if you're only interested in global synchronization and so on, then graph spectral properties determine synchronization behavior. Sure,
because
that's
at
fine.
the end of the day, you do relay stability analysis. So
So that's a very good point. Thank you for bringing this up. So yes, you do linear stability analysis, but the main difference here that this is a thing that is global, right? So here, that's an excellent point. Let's briefly go back to this. So if you look at things like master stability and so on, and using these tools to study synchronization, your goal is to study synchronization, right? So you want to understand what's the stability of synchrony. The goal of phase reduction is a global analysis, right? So in the sense that I have an invariant torus, and I don't care about just one point on the torus, but I care about basically the dynamics on the entire torus. And that's why I actually have here a secondary bifurcation, because my master stability for the other equilibrium would depend on the state. So here you actually do an analysis for an entire invariant set in your state space that includes synchrony, but is not limited to it, because you can study synchrony, anti-synchrony, and any other basically phase-locked state simultaneously. So in that sense, it has a more global feature than kind of standard, in quotation marks, approaches that are equally valid, but often enough they're kind of they have a more local flavor in their analysis, which is fair enough. If you're only interested in this, fine. But that's often enough the difference. Thank you for bringing this up.
Maybe you're aligned, I don't really understand like what's the black magic behind the stability analysis of this couple of oscillator equation. Like, how do you do that in practice?
In practice.
Yeah, yeah.
So there's two questions, I guess. How do you do phase reduction in practice?
No, more like once you have your phase reduction equation, like how do you do the stability analysis?
I mean, then you have a system on an n-dimensional torus, and you can throw your standard dynamical systems toolbox at it. What are all the equilibria? What are their linear stability? What are the bifurcations of the equilibria? But your n-dimensional system is an n-dimensional system. N is the number of oscillators.
First look at fixed point of your.
For example, or you look at more complicated dynamics that can occur in these phase equations. That would be my bonus material, heteroclinic cycles, chaotic dynamics, and so on. So that's another thing where a more global picture is important, because you can do analysis for equilibria, steady states, but once you want to quantify chaotic dynamics or more global bifurcations, then you need a more global picture. Does that make sense? Okay. I briefly want to touch upon the third question, and then I think it's time to wrap up. Is the question what happens with delay? And this is fairly recent work, so there's a bit of an outlook of what we can do. So again, just to kind of remind you, this is now an infinite dimensional system. So I have a coupled oscillator, an oscillator here. I have an oscillator here. I make the assumption that these oscillators do not have delay in them. So they have like finite dimensional differential equations. But I have a transmission delay. So all my delays are in the coupling, like in the coupling, which is kind of a reasonable assumption. If you think about the brain, then like the individual neurons, they're almost like close to each other. So finite propagation of signals doesn't matter as much as if you're like across brain regions and you have to go like from one hemisphere to the next. So that's kind of the idea, transmission delays and so on. That's a delay differential equation. So a delay differential equation is infinite dimensional, but there's a little trick that allows us to compute phase reduction to this, because you can rewrite the delay differential equation as basically an ordinary differential equation that is coupled to a transport equation. And the transport equation, that's an integral equation, takes care of your history. So rather than looking at this equation on the function space, you look at basically a PDE coupled to an ODE. And that allows you to do a phase reduction to arbitrary order. That's the main point of this paper. I don't have the reference here. I have it at the end. I don't want to go into this detail, but the idea is the same thing as before. For this kind of transport equation ODE, we have Finish-Hill theory that says there is an invariant torus. Importantly, this invariant torus, because the object that we start off with, the uncoupled system, is a finite dimensional torus, Tn, number of nodes, n, right? Finite dimensional, nice. Now, as soon as we crack up the coupling, we basically put this finite dimensional torus into an infinite dimensional state space, but the finite dimensional torus persists. That makes kind of our, this was not a planned joke. It makes our reduction infinitely more powerful, because we now have the dimension reduction not from some mn dimensional phase space to an n dimensional phase space, but from an infinite dimensional phase space to a finite dimensional phase space. And that means that instead of looking at phase equations that are delay differential equations themselves, we actually expect to get just a coupled ODE that describes the dynamics. That's actually quite fantastic.
Why is it infinite? I mean, even if you allow all sizes of
because
interactions,
you evolve history functions. So the idea behind DDEs is that you evolve a history function. So your state space is a function space, and your function space is infinite dimension. Because you have to, in order to know what happens, you have to specify the values of all coordinates for an entire history segment between 0 to maximal delay, or infinite delay. But that's the simple reason. But
this one piece, okay.
Yeah, but the phase reduction then is actually nice, because it's really a finite dimensional system where you don't have to worry about the DDE and all the technicalities, functional analysis, whatever that come to it. So you can do this in a systematic way. You have your coupled equations, and you can compute the phase reduction of this to arbitrary order. This becomes arbitrarily complicated, and I'm not saying that this is easy. The only way where we were able to calculate something is for, well, two coupled oscillators. Well, it's straightforward to generalize it to n, but that's kind of the mathematician's generalization. This is for two coupled oscillators with perfectly circular limit cycles, with isochrons that are straight lines, so there's no nonlinearity around the oscillator. So it's really the simplest case. The first order reduction you can compute for bent isochrons, but the second order just becomes a whole mess. So that's why, like, how to do this effectively in real world systems, I would love to have a computational approach that basically I plug in my system and it spits out the phase reduction. That's kind of high up on the wish list that I will never get. But for these two coupled oscillators, it works. So on the left, you see this is stability of synchrony, and this is the prediction of the bifurcation to first order. To first order, your time delay is actually just a phase shift. So it tunes basically makes synchrony, makes it that if you have a phase shift or a time delay that is within half a period or a quarter period forward, quarter period backward, you have positive interactions, you synchronize, and otherwise you anti-synchronize, right? But if you look at the solution, the color of the actual DDE, you can see that this is not the case. You have some wiggly line here, and this is for reasonable coupling strength. This is now the same thing computed for the second order phase reduction. So this is a solution of a one-dimensional equation, right? So this in the background is a solution to infinite simulations of an infinite dimensional system. These blue lines are computed from a one-dimensional algebraic equation. And they actually match quite nicely. They capture the shape quite nicely. Here it gets past one period, it gets a little bit weird, but I think it's a good start. So bottom line, it works. What's of course on the to-do list is kind of to do the same thing here. Yes.
What is the equation?
So the equation here is just two coupled oscillators. So basically two square.
The algebraic one.
Huh?
The algebraic one that you meant.
Oh, this is a fixed point equation. So that's basically you end up something along the lines of this is you have two phases, theta 1 and theta 2, but because the symmetry, only the phase difference matters. So you write some psi is equal to theta 1 minus theta 2, and write down psi dot, and that evaluates to nothing. And then you get some kind of a coefficient here of say cosine cos of psi plus a first phase shift plus b of a cos, or cos of sine, doesn't matter. I mean, that's psi 2 psi plus beta, and these what you get is these beta, b, alpha, and a explicitly in terms of the delay and the other parameters you have in the system, and what you want to calculate, stability of say synchrony. Synchrony corresponds to psi is equal to 0. So they basically then you can linearize around the steady state. I probably shouldn't have written this more so generally, because you always want to have psi is equal to 0 steady state. So there's some coefficients of probably sine without this, sine without this, and these coefficients are quite simple. It doesn't matter, but it's basically an equation of this type that you basically just look at the stability, linear stability of psi is equal to 0, so exact phase synchrony for a one-dimensional equation. And then you can calculate linear stability. Okay. Yes.
This result that the invariant field persists when we get these delayed interactions, is that? I get whether that's holds for this particular system or in general.
So in general, there's a generalization for Fenichel to semiflows, which covers the DDE case. So the persistence of the invariant manifold is not too much the issue. You can just hand wave and say general theory says the invariant manifold persists up to a critical coupling strength. Of course, you have no idea what the critical coupling strength is. But the main contribution then there is how do you compute the dynamics on this? And there, basically, we generalize some approach of basically calculating embeddings and phase dynamics simultaneously, and solving these conjugacy equations becomes then complicated. So it's not so much the fact that you have an invariant torus, but it's more the fact that you can actually compute what the phase dynamics is, which gives you a translation of how does your time delay actually go into these kind of coupling functions, into the sine and the cosine. And that's kind of the question that needs to be worked out. right? So you probably get a picture of the same way with some interaction functions, but now the interaction functions probably also depend on the time delay, both the Fourier coefficients as well as the phase shifts. And this is something that well, I haven't seen anyone compute before, because typically people do this approximation here, that if I have a delay coupled system, then my delay corresponds to a phase shift. So I somehow always substitute, like I just don't care about the delay. I always care about the phase shift. Here, of course, it says that's true to second order, but not to higher order. And it doesn't, for intermediate coupling strength, it doesn't capture even the synchronization dynamics of two oscillators. So that's the nice thing, that you can compute things explicitly, these coefficients, these coupling functions, in terms of the time delay as well as the physical parameters of your system. So that's should be done, right? But it's kind of semi-straightforward to it's more bookkeeping to generalize this calculation for two oscillators than for three, and for non-trivial networks. Okay. I think that brings me to the end, because we're already past noon. So there's a paper about heteroclinic dynamics, so more complicated than just looking at stability of equilibria. I'll skip this. So I just want to give a couple of conclusions. So the main thing for me is that somehow, on the one hand, there's kind of people who kind of say, okay, I take Kuramoto, I generalize this to higher order interactions because I have a particular tool that I can use. So for example, I can use spectra of hypergraphs, whatever that means. I'm not going to go into this, to calculate synchronization behavior. That's cool, right? So you take your combinatorial structure and you use a method that relates to the combinatorics of the structure to analyze synchronization. What I'm saying is, that's cool, because there's actually links like through phase reduction to physical systems. So that's an opportunity, in my opinion, to link somehow combinatorics of hypergraphs, whatever hypergraphs, classes of directed hypergraphs, to physical systems. So that's kind of really the pipeline. So it's not like, not like that I'm saying, oh, you guys who generalize this, that's not the way to go, but more like it's really a translational effort that we can make. Shown you, at least in pictures, that there's good approximation for dynamics, but it kind of also makes you think about whether directed, undirected hypergraphs, what's the right combinatorial object that captures these indirect interactions to arbitrary order? That's kind of a question more for people on combinatorics. Yeah. Of course, there's kind of this question. I still like to engineer a system. It's like, okay, I'm cheating, but like as a mathematician, my ambition is not that high. I just want to even see a physical system in which your analysis holds, which is already like. When you, I mean, I can prove whatever I see about this, the system, but when you then translate it like to something that is experimental, there's so many other things that it's non-autonomous, your system degrades and so on, that it somehow resembles the math is still kind of cool, despite being like semi-artificial.
How much of a string theory you have seen in experiments?
I'm a bit beyond it.
So just like to wrap up funding. We had a doctoral network funded that is kicking off now. Where I have the first PhD student in our department. It was funded by the project. We're starting the scientific work now. 10 PhDs across Europe who really want to exploit these connections between higher order interactions, physical systems, data, and the connection. I'm very happy that Fernando is part of this project. So that's cool. Despite the PhD students have just started, we have our first publication already. We kind of sat down with the colleagues as how do I explain this to my 2- and 4-year-old what daddy does. So we conceptualized a little kid's book that explains basically well, what a network is, what a hyperedge is, and what synchronization is in terms of soccer-loving bears. It's freely available, and huh? I mean, it's well, it's mostly cartoons, and there's a little epilogue that gives you a mathematical puzzle that is written in English. But my kids just love it for the bears, so I still have to press the button to get the 200 copies to the Vue, so whoever comes can pick up a free copy that will be lying around. But if you can't wait and you want to show this to your kids, this freely available on Zenodo for download. So with that, thank you very much for your attention. This is kind of the references. This is the funding, and do get in touch. And I'm around. I'm not too far away. So thanks a lot.
So welcome question. Maybe one or two more because there is a synchronization problem between Freeze and his kids.
Well, today is my kids' day, so I'm very grateful that my partner takes care of the little one so that I can be here. So thank you very much. Yes.
Maybe provocative question, perhaps. I mean, I guess the goal is to express this incredibly completely dynamical system into like something lower dimensions. So I'm wondering whether data-driven approaches could be something you could think about to help you, or to try to see how you could compete maybe with your labor.
I mean, they are like network reconstruction, also network reconstruction for kind of hypergraphs. So kind of you take a set of dynamical data and you want to understand what kind of interactions could have caused this. Is a thing.
I'm thinking about variational autoencoder, for instance, right?
Say it again.
I'm thinking about variational autoencoder, like I know to, like.
You have to tell me more about this.
Okay.
So I mean, like there are like data-driven techniques to kind of do phase reductions, but it's in general an ill-defined problem because you have to make assumptions in which space you look at these interactions, and that's really an example.
I guess that's precisely the point of this, neural network. They can give you like a latent space that's maybe lower dimensional, but it kind of figures it out by itself, right? And some people have shown you can actually find back animal tones in the system. I was wondering whether, I mean, compete with your bread and butter, so I'm not sure it's something that's
no,
I mean, but I don't know.
No, maybe.
I can send you paper what people do.
Okay, that'd be nice. So I'm definitely aware of the kind of network reconstruction where you say, okay, well, you have a phase reduction, you have a non-phase reduction, you have dynamical data. What kind of interaction structure could have given this? But I guess that's a slightly different problem than what you're talking about. Because that's kind of, like in general, it's an inverse problem that is ill-defined because depending on how you choose, what choices you make, you allow for different systems that give you the same dynamics. If they synchronize, I mean, there's like network reconstruction. Sorry to kind of use your question to talk about something else, but so somehow network reconstruction also depends on the data that you have. So if you have a system that synchronizes, I mean, you have no clue about the high order interactions because you just have local information around synchrony. So, when I think about network reconstruction, then I always kind of think about you need somehow ergodicity of the system, that somehow the trajectory samples.
Yeah, you can couple those networks with like evolutionary algorithm to tell you, okay, like go now in spaces you haven't explored.
Okay. So then you kind of influence the dynamics itself as well. So it's kind of a two-way system that somehow you have a controller that makes your trajectory go into a certain part of phase space and then evolves a bit, and you use this to. Okay, that'd be interesting. Don't know too much about this, so. Yes.
You've discussed this all the dynamic in a strictly deterministic setting. Wonder, is there any interest in considering it in a more noisy environment?
I mean, like I'm kind of the deterministic person. People have done phase reductions with or like what's the question? The question is like, what is phase when you have noise? When you have noisy attractors, can you still define the notion of space? Not space, phase. There's some work from physics community around Arkady Bikovsky that have done notions of phase for noisy systems. I think didn't Maxi Engel, who's now at well, your colleague, I thought he also did a bit of phase reductions for noisy systems. So there is interest for sure. Like this is well, like I can make it easy for myself and say it's a different complication that you throw in. We haven't considered, but it's
related to sort of physical systems.
yeah, but obviously it's a question. But then it's like, okay, well, these things about what is an invariant torus, like what is the invariant object that you approximate? Potentially, you need to go into the right space of distributions of kind of well. Take an approach of probabilities where your oscillator is, and then try to develop a notion of phase based on this. So yes, but it becomes more complicated.
And then let's thank Chris again.